have indirect band gap because you don't have alignment on this. And the reason why you need a direct band gap for photon absorption is because of momentum. Photon have no momentum, so you need to have excitation in a direct way. Whereas if you have momentum, if you have an excitation energy in terms of excitation that has momentum, then you would have the indirect band gap transition. But for photon, you don't allow this sort of, you only allow direct transition like this, direct band gap transition. So in the case of crystal with a direct band gap, you have the onset of the direct photon absorption like this. So you have transparent region, non-transparent region. But if you have a situation whereby you have indirect band gap like this, right? So here you cannot go directly to somewhere that at the same K value, right? You have to have a momentum transfer to move to this band somehow. So you would have something like this, and this momentum transfer can be obtained by your crystal lattice. This is known as phonon excitation. So you can change. So you have an extra photon momentum transfer introduced into this energy to make it go like this, and then you would have this absorption. And this extra knee here is due to phonon absorption. So electron conduction can have several ways, right? So here you have a material. Electron conduction can be produced by direct excitation in intrinsic semiconductor. Intrinsic means that they are inherently, there's a band gap inherent in the semiconductor. Extrinsic semiconductor means that they are doped, usually extrinsically doped to create this band gap, to design band gap. And you can control this impurity. So for example, N-type, you're using something that's have more electron than silicon or germanium. So gap in millivolt, right? In millivolt. So you can dope this thing and create different type of band gap that you got. Okay, create different type of band gap. So here is a carrier concentration, right, of different materials. So you have metal, semi-metal, and semiconductor here. Normally you're looking at semiconductor down here. You can also use semi-metal sometimes because they have very high conductivity and can respond to, semiconductor and semi-metal are very closely related to one another. You can still excite using a photon to create this excitation, photoconductivity this way. So here's the picture that you have. You have a list that with this you can create different band structure shift from this. So you have P-type, N-type, and this millivolts here correspond to the shift from the conduction band. So I'm plotting here. These are semiconductor shift of the Fermi level. So I'm plotting here. I'm plotting this way, and this I'm plotting about this difference from the conduction band. Okay. So you can tune. In other words, you can tune your valence band position. You can tune your valence band position or conduction band position here by adding this impurity, by lowering. If you want to lower your conduction band, you can add P or P-type donors. So you lower it by this amount, right? Lower the conduction band level of silicon, right? Or of germanium, you can lower a smaller amount by adding these materials. Okay. And this is a plot of direct band gap versus indirect band gap. So here you have what we just talked about, that you have a direct band gap transition, and then here in the case of silicon, it's kind of like this. When we are talking about direct or indirect band gap, we are talking about K-space transition. So here, you should think about momentum space, reciprocal lattice spacing, space direction. So here you have they are coincide with each other. Here it doesn't coincide the bottom, and this there still could be a band on top, but there's still energy level on top. They're just not the lowest one. So you have energy photon excitation. Your minimum energy will be this plus a phonon excitation. You have to excite this one. The energy you have to raise the electron to here. Plus, you also need the energy to excite the vibration of your lattice in a certain way. And this excitation of the lattice is known as the phonon. So you have energy of the phonon plus the energy of the direct transition to give you this indirect transition like this. Okay, so we have different material, right? So here is a table. It's a very useful table, particularly when people talking about nanosciences. How do you build quantum dots material? And here's the important thing. You talk about indium cyanide, gallium arsenide, cadmium sulfide, right? The beautiful material that you see that people show when the quantum dot idea come out was that they make it in a jar, right? They make it by laser, exciting the solution, and you've got this fine particle in the solution, and these are usually this material, this direct band gap material, and they change color because of this direct band gap, because you have photo excitation, right? Absorption of visible light, and they have beautiful color. It's because of this direct band gap of this cadmium. Usually, I mean, the first time these things come out are cadmium sulfide, cadmium cyanide material. You can see why they are so great. Well, because you can see cadmium sulfide 2.5 electron volt or 2.4 electron volt at room temperature. Cadmium cyanide 1.7. And what is this energy range? You remember 1.5 to 3.5 electron volt is the visible spectrum region, right? So these are exactly that generate the nice, beautiful color that we can see in a jar, right? If you have this particle in a solution, you just see beautiful color because they would absorb the visible light in a certain part of the region and leave the other light behind. And this is how you see the color. Okay, so they are in the visible spectrum, and this creates a lot of excitement in the nano world because of this quantum dot idea that you have direct magnetic excitation. And then you have in the early days, you have gallium arsenide, right, in the 1780s, is 1.5 electron volt. We're excited by this. Why people get so excited by it is because you remember silicon has an indirect band gap 1.2, 1.1 electron volt up here, right? And they found something that is very close to the silicon band gap, but it's a direct one. And this they found in gallium arsenide. Okay, so that's why in the early days, 1780s, people were excited because they found a material very hard to build gallium arsenide. That is very close with a band gap structure, very close to silicon, which means, what does it mean? It means that it suggests that they can easily integrate into the silicon device fabrication by just changing the material science, which is basically gallium arsenide instead of using gallium arsenide instead of using silicon for the material. So now all your little CD player